is Colin Gordon, who will talk about Java method local inner classes and why they are unsound. Okay.
All right. Hi. Thanks for the introduction. So I'm going to talk today about something that we stumbled across in some work I'm doing with Marco and Nick, who are on the slide here but couldn't be here in person today, along with a few other folks. The context for this is basically we are working on an interesting object calculus, which I won't actually talk about today. But the thing that's interesting there is that in that calculus, the creation of new objects and new types is a little unique. Basically, all of the class definitions end up looking like they're located at the allocation sites, which ends up being fairly close to Java's method local inner classes and how those work. And if you're wondering what is a method local inner class, I'll say what it is in a minute. But as we were formalizing this, it turns out there are a couple wrinkles that we weren't expecting. We didn't see these written down anywhere. And so we did, we have solutions, but we kind of did what is natural to do and asked, okay, we're seeing this interesting scenario in this core calculus. Let's see what mainstream languages, heavily used languages that have analogous features do in analogous situations. And it turns out that, at least for Java, it does things that are not quite what we would expect. Right? So first of all, let's talk about what even is a method local inner class. So the name is suggestive, but it is a little bit of a niche feature. Not everyone is aware that Java lets you do this. Java lets you declare a class inside a method. Right? So on the right here, we have a method tasks, and we have a method local inner class here, a specialized runnable. It has constructors, it has fields, methods, whatever else we want to throw in there. And usually when we do this with not to keep the instances of this type purely local to the method, but because we usually use this to implement some external interface, inherit from some external class. But by virtue of it being named, we can actually use the name and construct it multiple times. It's a little more convenient than if you tried to make this happen with anonymous inner classes directly. And now if I gave you like the featherweight Java paper and said, okay, go add this to the basic featherweight Java calculus and prove that it's sound, you wouldn't hit any problems. Right? So this feature by itself makes a lot of sense, it's convenient. So where do we hit the problem? And the problem crops up when we have these things interacting with generics. So Java allows a combination of a few particular things that play a little poorly together and don't result in any warnings. So I'm going to say what they are to give you a sense, and then we'll talk about a detailed example. So Java lets you have a non-generic method local inner class, like on the previous slide, but it lets you have them in such a way that they somehow capture a dependency on a method-bound generic parameter. So most of us don't write a ton of Java that does this, but Java also lets you bind generic parameters per method invocation. Once these objects escape the local method, they are no longer, it turns out, tied to the particular choice of method generic parameter that they were created under. And because it's non-generic, the Java compiler doesn't give any warnings about casts or instance of checks with that method local inner type. So hopefully I've at least convinced you that there's something a little bit interesting here in this possible interaction, but I'm going to do an example. But ultimately what this lets us do is we can mix up instances of this method local inner class from different method invocations that use different generic parameters, and it leads to some confusion. Right? So here's an example. We could make it more minimal, but I think this is a little more readable. So down at the bottom here, we have this just generic container of x's. You could use list, you could use any other generic type for this example to work through, but we're just going to call it a foo_x. And then up at the top here, we have a class that has a static method that is this problematic generic method, and then we have some main code that's going to trigger some problems. So first thing we do in the static method m is we have an anonymous inner class. It's called myFoo, and it extends foo of x. Right? It happens to capture this x argument to the method, but that particular part's not super critical. The thing to pay attention to is this myFoo is not generic in and of itself, but it's sort of implicitly generic because it does depend on the choice of x here. So, choice of, yeah, sorry, actually there are too many x's here. It does depend on the choice of this generic type parameter to the method. Right? So, the actual code in this method, there's only 2 lines, and these are kind of the pair of lines together with the way we set up the definition of myFoo that end up being a little bit funny. So the first thing we do on line 4 there is we check, we have this other object, right? And everything in Java is an object unless it's a primitive. And we can ask, is this an instance of myFoo? Right? Now, certainly the first time we call this method, we can't have any myFoos before. So the first time we call this method, this will not be an instance of myFoo. So we allocate 1 and we return it. If we call this later and we do pass in a myFoo, well, the instance of pass check will pass. It will be a myFoo. And then we cast it to a myFoo, which should work because we just checked that it is a myFoo and we return that. The problem is JVM generics are erased. So what happens here is this instance of can be compiled and it runs, right? And it basically checks, is the class table for this object myFoo? And it can make that check and it can succeed, but because the generics are erased, it doesn't actually check if this is a myFoo from this invocation of the method with this choice of the generic parameter, or if it's a myFoo from a previous invocation with a different generic parameter. And the same thing happens with this cast, right? Same problem again. We cast a myFoo, and the cast succeeds because it has the right class table. But again, the generic parameter is erased, so that part can't be checked. But this code compiles and runs without any compiler warnings. No warnings, no errors. So what goes wrong? So let's talk about this main method. So first thing we do in this main method is we make one call to this method, and we call it with an integer. For that first object, we just pass, it could be anything, so we pass the string anything. We go through, we get to line 4. The string is clearly not a myFoo, so we allocate a new myFoo. It happens to capture this 5 that we passed along the way, and we end up with this sort of object graph on the left here, right? So we have one myFoo that sort of implicitly is supposed to be a myFoo for integers, and it holds 5. Right? Now we do the weird part. We call this method again, but we call it with a different generic parameter. We call it with strings instead of integers. And we also switch which random object we pass in. We pass in now this first myFoo that we got out. So it goes in here on line 4. It now is an instance of myFoo. So that gets negated. So instead of allocating a new one, we get to line 5. We cast it to a myFoo, which it is. And we return that R1 argument as the result, which means that R2 now points to the same object, even though its type says it's supposed to be pointing to a container for strings. It points now to a container for integers. So essentially what we've done is we've implemented a cast from foo of integer to foo of string. But if you tried to do this cast directly in Java, it would complain. It would say, hey, we can't check this cast. Or if you tried instance of with one of these types, it would say, sorry, we can't check this at runtime because of the generics erasure. So it's also worth pointing out here, so what do we mean by unsound? We mean unsound in the sense that there are features of Java that we'll get to that lead to this not corrupting any memory. But this violation, right, this fact that we haven't actually gone out of our way to use some of those particular features of Java I'll talk about later, but we have something that says it should be a container for strings, but is pointing to a container for integers, right? So this is what we mean by unsoundness. And if we continue execution, line 10 works, right? So line 10 is using this object as it was meant to be used, as a container for integers. It tries to get the integer out. We print 5. Everything's fine. And then on line 11, when we try to get the string out of this thing that actually contains integers, we get there a class cast exception. So what's going on here? Right, so again, this is a combination of a few things. So my foo is tied to a generic parameter. It cannot have its generic parameter checked when we're doing cast or instance of. And casts to and from, likewise, instance of checks with this, do not yield errors or warnings. But curiously, if you go and just tack on a bracket X on the definition of my foo, suddenly you get errors. So somehow it seems like if this is explicitly generic, the compiler kind of does what we would want. It gives you a warning. But since there's not literally a generic argument list on the declaration of my foo, it's treated as non-generic despite sort of relying on this method generic parameter. So I mentioned earlier that that example was just sort of had this foo type just sort of as a placeholder for generic kind of container. But you don't actually need that. So you can trigger this all sorts of ways. I won't walk through this one in detail, but you can see the first line of this method m here. We still have a class myfoo. It still depends on this method-bound generic parameter type x, but we're just relying on it being an object. So we don't even need the generic container type. It just escapes as just a regular old object. It can come back in as a regular old object as far as the static type system is concerned. And we have the same instance of and casting trick in there. So a natural question, though, here is, on the previous slide and here, we end up in this case where we have a variable that points to the wrong instantiation of my foo's sort of implicit generic parameters. What actually throws the exception when we run these example programs? So, courtesy of Compiler Explorer, there's some JVM bytecode down here. It looks like it's a little less readable on this format than when I prepared the slides, but we'll go with it. So this is the JVM bytecode for the two print lines, the last two lines of that first example, where we first print the value in the integer container and then print the value in the so-called string container that actually has an integer. And you'll notice that the second one's a little bit longer, and it's not just because the return is down there at the bottom. So the first call is going to call the object overload of print line, right? So there's a bunch of different overloads for print streams output methods. There's one that just takes object and just calls object.toString and prints that. And when we do this with an integer, that's what gets called, right? Now, the second time, we call a different overload. We call a string-specific overload. And in that case, because this is the output of a generic parameter, the compiler inserts an additional check cast instruction there. The reason for this is because Java also has this feature that now when I talk to students seems a little bit lost to the sands of time, which is raw types, right? So Java has this feature where even though it has generics for backwards compatibility, you can take a generic type like list of t and just treat it as a list and put whatever you want in it. And the compiler will, in certain circumstances like this one, say, we're fetching something out of this generic type, but maybe somebody used it, this object at a raw type somewhere else in the program. We'll stick in a check cast, and that sort of saves things from going too wrong here. But the interaction of these features is totally non-obvious, especially since we don't really teach anybody raw types anymore. They're not really discussed in modern introductions to Java. And I regularly talk to people who are a little younger than me who don't even know they exist. So this is weird, right? And so this is what we are calling an unsoundness, right? Because this is not the expected behavior. And in general, this failure point of this check cast that gets inserted later could, like other raw type situations, be arbitrarily far away from where we mixed up these generic parameters, right? Now, a natural question to follow up with is, okay, so that's Java. Java is not the only language that runs on the JVM. And the other languages that run on the JVM want to interoperate with Java, which has this feature. It has method local inner classes. So the other robust, mature implementations of languages on the JVM also support some form of method local inner class as well. So what do they do? Do they do this any better? Well, Scala is an interesting case. Scala 3.0 does exactly what Java does. Works exactly the same way. No warning, no error, same code gen. Scala 3.4.1, somewhere in there, they added an error. It's not the clearest error. It says that you can't check the cast that we use, and it just says you can't check the cast because it's a local class. But of course, it's not just because it's a local class, it's because it's a local class that also depends on method generics, right? If there were no generics happening in this example, the cast to my foo would have been totally fine. So, okay, great, that's Scala. How about some other languages? How about Kotlin, right? So Kotlin's another somewhat younger but growing language on the JVM. So here's a direct transliteration of the first example into Kotlin, and you might notice there's a little squiggly there. There's a little red squiggle. And it turns out that's because Kotlin does actually give you warnings about this. It does say error cannot check for instance of arrays type myFooX. And this is interesting because we didn't declare myFoo as explicitly generic. We did exactly what we do in Java. But Kotlin caught on, hey, there's a dependency here on this method parameter. And so Kotlin actually seems to track this internally, as do newer versions of Scala, and notice, hey, this has a dependency. We need to at least give a warning. Now, you will notice that there is no squiggle on line 10, which is the actual cast. So it gives us a complaint on the instance of equivalent, but it doesn't complain about the cast. If you really wanted to, you could still trick Kotlin by doing the cast, caching the exception, and using that without the instance of check, and then you could get it to work without warnings. So it's not perfect. Kotlin's also interesting because it actually has two kinds of casts. It has so-called safe casts, which are not safe because you can't misuse them. They're safe, quote unquote, because they don't throw exceptions. So they have an as question mark cast operator, which if the cast would fail, instead of throwing an exception, you just get null instead. And in that case, you no longer get an error, but you do get a warning that, hey, this cannot be checked. But again, there's still kind of this hole here with just the regular old possibly failing cast. If you're willing to catch exceptions, you could still trick things, right? So ideally, Kotlin has enough information here. It could issue an error for the cast as well. So what do we do with this? The core issue here really is that there's a method local type that depends on a generic parameter that gets erased, right? So instance of with these method local inner types cannot be checked. Casts with this method local inner class, because it depends implicitly on a generic type parameter, cannot be checked. So we think that the instance of and or the cast should yield an error, or at least a warning, although we think it should be an error, because you just can't perform these checks, right? And we can see that Scala and Kotlin do track enough information that they could give warnings for all of the right cases, right? Kotlin gives the right warning for 2 out of 3 possible sources of unsoundness. Java does none, Scala does 1, right? So if we just change things so that Kotlin actually performs 1 extra check during compilation on that unsafe cast, then Kotlin would be sound, and there's no fundamental reason that other languages can't do the same and be just as thorough. So that apparently went a little faster than expected, but that's all I had planned to say. Okay.
Question.
Thank you. Thanks for the talk. The erasure semantics of Java was an implementation hack done for political reasons so that Sun didn't have to change the virtual machine. So the real, and what you've discovered here is places where in the implementation, the compiler, they should have done these tests and didn't.
Yeah.
The question I have, is there a language design issue, or is it just don't do implementation hacks that don't model the actual language? Does that make sense?
My personal feelings about erased semantics aside, which I suspect agree with yours, if you have made that choice, you can make it sound if you have the checks in the right places. It just seems to be one of those cases where syntactically this method local inner class doesn't have a generic parameter list attached to it. So it gets treated like it's not a generic type, even though there's this extra way of capturing a dependency on it.
For example, they could have done the implementation where there was something like an instance variable which held the value of the generic, that type, so that type could actually be used. And
oh yeah,
it would be useful to know that design with inner classes really is sound. I gather there's a, what is it, the Waddler stuff, the featherweight Java with inner classes, and I don't know whether it deals with these issues. I suspect it doesn't get quite that much.
Yeah,
depth,
we haven't seen any formalization of something that mixes both inner classes and generics, which is how we ended up sort of poking in this direction. Because doing the proof for the calculus we're working on, we ran into some kind of funky issues, and our settings are different enough that our solution's a little different than what we're recommending here. Dot? For, that's a good point. I would have to go sit down and look at the details again.
So which one? Do you mean dot?
He means dependent object types. Which?
DOT, right? Dependent object types? Yeah.
Yes.
So Guillaume Martre, who is on the Scala team, he wrote his thesis on featherweight Scala, which is a bit closer to the actual Scala. And I don't think he formalized local classes, but I think the main reason is that they're easily desugared into top-level classes where this problem doesn't occur. Because then
if you did the desugaring, you would basically add this parameter explicitly, right? Which might actually, we haven't looked at the code, but we suspect this is what's happening in the Scala compiler and the Kotlin compiler.
So that might be where the error is coming from in the Scala compiler, right? And it's probably the easier way to check for this, to first desugar and then do the check, right?
Yeah, that would be totally equivalent to tracking it as a property of the anonymous method local inner class too. Totally.
Right. Okay. So can you say again? I think I missed it. You said that Scala gives the correct warning in one case, but not in some other cases.
Scala. Whoops.
Yeah.
So Scala does flag the warning. It flags the cast, not the instance of. And in some sense, you could argue the cast is the more important one. But
it doesn't flag the instance of.
It doesn't flag the instance of.
It's actually a problem. Mm-hmm.
Yeah, but I mean, that would be probably not what you're expecting and sort of be surprise semantics. But that alone you can't get this kind of unsoundness out of. You need the cast to work too.
Right.
So it does at least flag the cast, but the wording is a little like they wrote half the error message. Because it depends on not just it being a local class, it's also got to be because it's generic. Mm-hmm. Because a cast involving a local class that really has no direct or indirect dependencies on a generic parameter, the cast is fine. You can do that, and it works just well.
Doesn't that mean that the Scala inner classes are nested inside classes, not nested inside objects, or in this case, activation records? Because you've got the issue that you could have two classes. I mean, the question is if you have two instances of one of these things from different method invocations, should they or shouldn't they have the same type? And that's a choice. And another choice is if you have two of these things
which I was going to say almost everything has to be nested, I think, inside a method invocation, even if that method invocation is in its pseudo method resulting from a constructor. But you kind of think of it as being nested inside an object or an instance of an enclosing class for the non-static, because all these are non-static inner classes. Mm-hmm. Again, should two classes nested inside different instances be the same time?
So
clearly, if you talk like this, Gillard should manifest, and he just has.
So, as you might imagine, as one of the people responsible for this mess, I have a lot to say about it. So there is more than one. Usually, these train wrecks are a result of more than one mistake, and the first mistake is the one that James just mentioned. And the beta people had done this in beta years before and knew that nested classes are properties of instances and not of classes. And some of us at Sun knew this, but the people who actually did the first cut of inner classes did not. And once it was there, it's unfixable. And what Kim called political reasons, otherwise known as compatibility for your actual customers who are not academics. And so there was no way to actually. Yes, yeah, and so these things, are cannot be fixed. But once I saw the title of your talk, I understood what the problem was, and that's a fine thing. My other meta comment is, as you say, no one seems to have analyzed this particular problem because one version of featherweight Java looks at this and one doesn't. And this is the problem with all the formalizations that have occurred, is because unless you have a formalization that does the entire system as it is actually done, which means it does class loaders and reflection and inner classes and serialization and all these things at once in one system, thank you very much, good luck doing that, then all your proofs mean precisely nothing. And that's the problem, right? You can show that something is sound in some fictional world, but it doesn't tell you anything about whether it's sound in reality.
Yeah, I mean, and what you say is exactly true, and it's true of all the other cases of this language feature and this language is unsound. It's, like you said, it's always the same thing because the real languages are so enormous that
is the problem.
It's a Herculean, unmanageable effort to try to formalize all of those details, for sure.
All right, any other questions? Just a quick remark. You mentioned at some point that if Scala kept track of generic parameters, it would be fine. And if there was no generics involved, it wouldn't be a problem. But that's actually not true. Because in Scala, you can use type members, and you can have path-dependent types.
Okay, that's
and
fair.
so you could get exactly the same problem without any generic parameter.
So I would argue that if it depends on a type member, then it would be a kind of dependency on a generic parameter, right? It would depend on some. It would depend on some type that could come from a different instantiation.
It would actually, yeah, sure. Right. Yeah. Okay. Thanks. Okay.
Thank you.